Hey, what's going on here? Concyclic points and cyclic quadrilaterals. Have you ever seen anything like that before? Well, let's have a look around the screen here. I've got a quick question for you as usual. 3 is okay, but what about 4? What's he on about there, mate? 3 points. Can you always draw a circle through 3 points, but not 4? This one worked. Hey, but D didn't make it on that circumference there. So can we get a little bit better understanding about how 4 points might form a circle or be concyclic? So concyclic, back up here in the title, means the points all lie on the circumference of a circle. And a cyclic quadrilateral, you might have guessed, is a quadrilateral, come down here, where you can join all the points on the circumference of a circle, and the quadrilateral is formed by those points. So a cyclic quadrilateral is a quadrilateral in which the 4 vertices all lie on the circumference of a circle. So these are interesting quadrilaterals here. So let's just go back and answer the question. If you have any 3 points, how would you describe, let's say X, Y, and Z now, how would you describe the fact that you can draw a circle through any 3 points? Let's have a look. What is a circle? A circle is a locus of points, where you would look for points which lie an equidistant from a given fixed point. So let's do it for these points. Let's find a point which is equidistant from Y and X, so it's on the perpendicular bisector. And then, so that lies equidistant from Y and X and from Y and Z. There's another perpendicular bisector. So it's always possible to find this point equidistant from all 3 points. Okay, so you can also do this here, and it will lie, that will go through there. Do you remember that? The orthocenter, the centroid, and all those previous triangle results. But can you do it for 4? Not necessarily so, is it? Because you might do the perpendicular bisector here, perpendicular bisector there, and they will intersect, and then perhaps a perpendicular bisector here. But over here, it may not intersect. Well, that's what we're going to look at now. Can we determine the properties you need for 4 points to be concyclic or form a cyclic quadrilateral? So just give you some idea there. Okay, so that's what we're about. Come on down now and see what I've got for you here. Screen clippings from Hayes and Harris publications there of the latest textbook in SACE, a pre-specialist, just coming in here. There we are. 4 points are said to be concyclic if a circle can be drawn through them. Or you can talk about a cyclic quadrilateral where the 4 vertices form a convex quadrilateral, and then those 4 points must be on the circumference of a circle. So how about that? Is that clear what we're doing now? So you might write that down as a definition. And let's have a look at, can we find something that defines a cyclic quadrilateral? How do we tell that you can draw a circle through it? We don't want to try and do the perpendicular bisectors. You can't do a construction. It might look as if it's working, but it might miss out by a tiny tad there. So what we've got to do is do some deductive reasoning here to define a cyclic quadrilateral. Deductive reasoning. No numbers, no values, no measurements. Okay, we're going to say the opposite angles of a cyclic quadrilateral are supplementary. So if you can show alpha plus beta is 180, then that makes the quadrilateral cyclic. That's a theorem. Can we prove that? We need to have some rule here, some deductive process by which we can determine whether a quadrilateral is cyclic. Okay, come down, let's have a look at the proof of that now. Okay, so here we are, here's the proof. Let's start with a cyclic quadrilateral, A, B, C, D, all points lying on the circumference. And if we join OD and OB, we can see those two are equal radii, but more than that, we're joining it to the centre. So the angle at the centre is twice the angle at the circumference. So if we call angle DAB alpha, this one in here, DOB, is 2 alpha. And if DCB, here it is beta, then the reflex angle at the centre, twice the angle at the circumference, subtended by the same arc, is 2 beta. But we know in here, the sum of angles at a point, or one revolution, 2 alpha plus 2 beta, is 360 degrees. Divide both sides by 2, and we have our result. In other words, in any cyclic quadrilateral, we can do this sort of deductive reasoning and come with the result that the opposite angles of a cyclic quadrilateral are supplementary. So therefore, what's left, the other two angles have to add up to what's left of 360. Sum of angles of a quadrilateral is 360. So if those two are supplementary, these two must be as well. Okay, get the idea. So we've just cracked it there. We have a test now from this deductive reasoning for whether 4 points will form a cyclic quadrilateral or whether the 4 points will all lie on the circumference of a circle, which is called concyclic points. Okay, come down, let's have a look at some more stuff of this. So here we are. Here's an example. Find x in this cyclic. It's cyclic, isn't it? All the 4 points lie on the circumference of a circle. So this one plus this one, we know, must equal 180. We usually put this reason in brackets, but they've stated it out there. And so we can find by simplifying this expression, 2x plus 36 is 180, subtract 36 from both sides is 144, divide both sides by 2, 72. We can actually find the required angles here to satisfy that x and x plus 36 in a cyclic quadrilateral. Okay, some little problem solving like that, fairly easy now. And here's another one though, here's another little test. If a pair of opposite angles of quadrilateral is supplementary, the quadrilateral is cyclic. Well, it's the same test. We're going to call it a cyclic quadrilateral now, rather than concyclic points. So have a look here. Prove the converse of the opposite angles of a cyclic quadrilateral theorem. So in other words, if they are supplementary, then the quadrilateral is cyclic. Okay, we've been sort of just hinting at that. So if you start with the cyclic quadrilateral, let A, B, C, D here, A, B, C and D be a quadrilateral, and we're going to say that BAD here is 180 take alpha. If this is alpha and this one's cyclic, ABED is cyclic, then you know that that one and that one are 180 and 180 take alpha. Now, if we extend this and make a bigger quadrilateral, you can say this one is cyclic, but what we want to do is investigate A, B, C, D outside there. So we've already said alpha and 180 take alpha, we've talked about that. Now, if you were to say ED, here, let's have a look at ED. ED is parallel to CD. Okay, if you make this alpha and say, well, okay, that's alpha, then they would be corresponding angles, and E and C would have to coincide. Okay, so to make a quadrilateral out there, the sum of angles of a quadrilateral are supplementary, opposite angles, sorry, of a cyclic quadrilateral are supplementary, C would have to be alpha and E would have to be alpha. E and C would coincide. Do you get the idea there that what we're doing is saying it can't be out at C to make a quadrilateral outside there if you have this one in here. So it's a bit confusing, this proof. You might have to look back through that. And we're saying sort of the converse, the opposite thing here now, that if you have a pair of opposite angles, sorry, not equal but supplementary, then that must be a quadrilateral. So the converse of that theorem must be a cyclic quadrilateral. All right, so I'll leave you to have a look at that and just have make sure you understand what's going on. The idea that C has to lie back with E if you're going to fulfill that theorem of opposite angles of cyclic quadrilateral are supplementary. All right, come down now and let's have a look at some results here. And what we're looking at here is if you have, of course, a cyclic quadrilateral A, B, C, D, we can say these two angles are subtended by the same arc, and we've had that before, and we can use that result in any cyclic quadrilateral. So there's quite a few results that are going to be relevant now. So let's have a look here. If a quadrilateral is cyclic, if a quadrilateral is a cyclic quadrilateral, if one of the following is true, we can have those two add up to 180, and that's what we've been doing. Or we can use the converse of the angles in the same segment theorem. We've got CD here, what I've just mentioned up there, subtending angles at A and B on the circumference. Well, if you subtend equal angles there at A and B, and they're subtended by the same arc down here, then what we're saying is you can have a circle, because that's the converse of the angles in the same segment theorem, isn't it? One side subtending equal angles at the other two vertices. So it's like saying, well, if that's true, a circle could be drawn, because these would be angles in the same segment. So what we're looking for is another way, what I've just mentioned up above here. Let's just go back up here. We're looking at, if it's cyclic, that's going to be true. So in the converse of that, if we don't know the circle goes through there, but we've got this behaviour subtended by that same arc, we can say it must be a circle. There must be possible to put a circle through those points. So it's the converse of the angle subtended by the same arc theorem. All right, so we've got two tools now. Two tools to determine whether the 4 points are concyclic, or whether the 4 points, in other words, form a cyclic quadrilateral. Let's go and try and use that in some deductive reasoning now. So here's one. Triangle ABC is isosceles, so we've got that down there, with AB equals AC, and Y and X, there they are, lie on A, B and AC, such that XY is parallel to BC. Now, we've seen this theorem before. Prove that XYCB is cyclic. XY, so you can put a circle through these 3 points. That's what we're trying to say. So if ABC is isosceles, now how do you go about proofs? Do you remember? You need a good, large label diagram, making sure all given information, particularly this isosceles, that you're going to say that this one and this side are equal. You make sure it's labelled. You want to prove that XYCB is cyclic quadrilateral. You've got two ways of doing that. The opposite angles are supplementary, or a line, one of the lines subtends equal angles up there on the same side. Okay, either of those two. So probably with this one, we might think of doing opposite angles. We'll have a look, because these 4 points aren't forming a line that subtends angles on the same side to check out. So we could just try to do the supplementary one. So we know that they said, what's the next step? Start with the first piece of given information, isosceles. So AB is equal to AC. So from that we can say alpha 1 equals alpha 2, base angles. Okay, now we'll also go to the next piece of information, do it logically. Next piece of information was the parallel lines here. So since they are parallel, you can say alpha 3 equals alpha 1, that's corresponding positions there. So therefore in here, sum of angles on a straight line, angle yxb equals 180, take alpha, that should have in there some angles straight line there, or some reason for saying yxb is 180, take alpha. You could say co-interior, couldn't you, with that parallel line? Could go straight there to say angle BXY, you don't need alpha 3 up there, you can say angle BXY is 180 take alpha co-interior with those parallel lines. And then, of course, the two that you're looking at are the opposite ones. Let's tidy this up a little bit here. It's getting a bit messy. So here now, what we want are the opposite ones. That one and that one add up to 180. Okay? And therefore, it is cyclic, opposite angles are supplementary. And we usually put as required. If we have achieved what the to prove line was, we usually put as required. All right, do you get the idea? You do need that strategy, and I've mentioned that in earlier presentations. A large, well-labelled diagram, that's quite often provided. All given info marked on it as much as possible that you can do. You start with the first piece of given information, and oh no, I've left something out here, haven't I? Adjust the to prove line, so look at the to prove line. To prove, does it need to be interpreted? Like, what will you try to do? Here you'll try to prove opposite angles supplementary, or a line subtends equal angles on the other side, on the same side, sorry. Then start with the first piece of given, first given info, hard to write on the screen here, and just proceed through. Proceed to the next. And with circles, of course, watch out for equal radii and a few things like that. And you work towards the end of the figure that you're trying to say something about. So there is a strategy. Don't just look at it and have a guess. There is a strategy. Okay, come down and let's see some of that in action now. So here's some exercise from Hayes and Harris. And what I want you to do is to pause the presentation, have a go at the problem, and then watch me do it, and then move on to the next one. Okay, so let's have a look. We're trying to prove the opposite angles of cyclic quadrilateral theorem using the following steps. So we're going to do another proof. For the given figure, find angle DOB. So angle DOB, we'd say angle DOB equals 2 alpha. Angle at the centre theorem, because that's a circle. And then reflex DOB, angle DOB, reflex, so let's put it there as reflex, equals, again, this one is twice this one, subtended by the major arc here is 2 beta, so that's still the same theorem, angle at the centre theorem. And then we can say 2 alpha plus 2 beta equals 360 degrees, and that's some angles at point O, which is the centre. Therefore, alpha plus beta equals 180, and we can see that as required. Okay, there's the first one. So pause the presentation now and have a go at this one. Copy the diagram onto your paper and then watch me do it, and we're going to go through all the exercises the same way, so you'll see how you're going. Okay, prove the opposite angles of a cyclic quadrilateral theorem using this figure. Show how this can be done. Okay, so let's have a look. We've got a well-labelled figure. We've got not much information on it, but of course with a circle, our first piece of information might be equal radii, mightn't it? So let's have a look. This is O, we'll label that O. AO equals BO equals CO equals DO, and this is equal radii. Therefore, we can say angle ADO equals D, base angles isosceles triangle, and then also here we can say angle BAO equals C, so that's base angles isosceles triangle there, and angle CBO would be equal to C. Again, base angles, and just come down here a little bit. Yep, just a little bit more. Oops, too far. I'll come back. Okay, and then here, angle DCO, so that's this one in here, will be A, and that's going to be, oops, I made a mistake here, CBO is B. Right, so in here, this is B, isn't it? B, and DCO is A. Again, base angles, isosceles triangle. They're all four of them are isosceles triangles. So now what can we say? Let's add up all the angles around the quadrilateral. So we've got, let's start with the A's, 2 alpha plus 2 beta, or it's really B, plus 2C plus 2D is 360 degrees, sum angles of a quadrilateral. Okay, therefore, what can we say now? We can say that 2 alpha plus beta plus C plus D is 180. And let's come and look at the opposite angles now. The opposite angles, here's a pair. That is angle DCB, which is an alpha plus beta. Doesn't equal angle DCB, hard to write on the screen here, plus angle DAC equals 180 degrees, because that's a AB plus CD one. As required, because that's supplementary, summing to 180. So just note there that those two angles, or you could use these two, and the sum of those two is an A plus a B plus a C plus a D. Okay, do you get the idea? We have to work through there. We're using the given information, then going on and trying to work out theorems that result from that, or working with theorems that relate to that. Okay. So pause presentation, let's try these now. Okay, so we'll just come down here, pause the presentation, and then I'll go through these. All right, so let's have a look. Find X giving reason for your answer. Well, A, B, C and D are on the circumference of a circle, so therefore X equals 180, take 73, op angles cyclic quadrilateral, and so that implies X equals 107 degrees. Okay, same thing over here. ABCD is cyclic, so we can say 2x plus x, opposite angles are supplementary, and we'll put that op angles supplementary. Therefore 3x is 180 and x is 60 degrees. Okay. Up the top here, what can we say? Well, this time we've got parallel lines. Okay, so that might help us. Let's use the cyclic quadrilateral first. So we can come down here and say angle DCB equals 180, take x, op angles cyclic quadrilateral. So that doesn't help us solve it yet for x, but then we can say, we haven't used the parallel lines. Remember the process. Use each of the pieces of given information, try to make a deduction from it. It's called deductive geometry. So now what can we do? Yes, this one and this one are co-interior. So we can say 2x takes 70, that angle, plus 180 take x, that bottom angle we just worked out, must equal 180 degrees. They are co-interior angles using that straight line, using parallel line given information. So let's add these up. 2x take x is x, neg 70 plus 180 is 110, then and that means that will be equal to 180, and therefore taking 110 from both sides x equals 70 degrees. So it's quite an easy strategy. You've got to think about it. Use one piece of given information after another. All right, so pause it there, mark your work, and now try these two. And then I'm going to keep going and show you the answers then. So coming down now to D and E, a little bit of room needed here. Okay, so again we have a cyclic quadrilateral, A, B, C, D. I'm going to use that first. And so here what we're going to say is this angle in here. So where can we go? X is there, and we've got this angle here, and so we want to work out this one here. And so if this quadrilateral is cyclic, there's a couple of ways of doing it. We can say here that this angle, angle DCB, equals 180 take X, op angles cyclic quadrilateral, cyclic quad, and then these two, 180 take X plus 180 take X must equal 180. Some angles, should be some of adjacent angles right next to each other on a straight line. So we've got that result. Because we needed to use this, I chose to use the cyclic nature first, and then that one. You can do it another way, the other way. Okay, so now this implies adding the 180s, 360, take 2x equals 180. So subtracting 360 from both sides, neg 2x equals neg 180, which implies x equals 90 degrees. Okay, and so that should have looked like a 90 degrees up there. Okay, so you get the idea. Let's do this one now. So make sure you've had a go first. So what I'm going to do is to start with, well, what piece of information? I've got tangent, and I've got a cyclic quadrilateral. I'm going to start with the cyclic quadrilateral. You could start with a tangent first. That doesn't matter. Let's look at the cyclic quadrilateral first of all. And so here we can say angle DCB equals 71 degrees, because opposite angles, cyclic quadrilateral. You're getting the idea of this? Opposite angles, cyclic quadrilateral. So we'll put 71 in there so we know what we've got. Now we need to use this tangent idea. The angle between a tangent and a chord. So the angle between a tangent and a chord theorem is that one there. So let's call this T. Angle BCT equals 47 degrees. Angle between tangent and the chord equals the angle in the alternate segment. So there's the chord, there's the angle between the tangent, and the alternate segment is over there, opposite the little segment here, the little segment on this side of that chord. So that's 47 degrees. Now we can say x plus 47 plus 71, all of this must equal 180 degrees, and that's some angles straight line. Okay, so now that implies x equals what's this? X plus 180. I'll do that first. X plus 118 equals 180, and therefore x is 180 take 18, which is 62, sorry. Okay, so can you see, you just work carefully through each of the pieces of given information and put it all together, and you've got to have a good knowledge of theorems though. Okay, so let's go on now and try some more of these. Here's question 4. Is ABCD a cyclic quadrilateral? Explain your answer. So here we'd say, let's look at the opposite angles. Yes, op angles supplementary. Okay, and in this one, let's have a look. Both of these are 47, so AD subtends equal angles at B and C. So yes, okay, because you can think now I could draw a circle through here because these are subtended by the same arc AD using the converse of that theorem. Let's look at this one. And here you can see that it's a no, because op angles not supplementary. Okay, they don't add up to 180. Okay, I hope you've tried all these. This is a rectangle. So all rectangles are cyclic because opposite angles add up to 180. Yes, and I won't write that down, opposite angles supplementary. And here, if you look at this, we can find this angle here, which is 180, take 113, which is 67 degrees. And so this one is yes, because it would be supplementary with that one. I'm not going to write all the reasons in. But this is sum of angles of a straight line, and then this would be supplementary. So you can see there, the exterior angle of a cyclic quadrilateral will equal the interior opposite, won't it? Because of these two theorems, both involving 180 degrees. Sum of angles on a straight line, and then opposite angles, they are supplementary. Let's have a look at this one, and we want an A, B, C, D, so it's these 3 points, 4 points here. So we might have to do a bit of work on this one. So first of all, what can we say? We can use this 80, which is outside, and say, what's this? We'll call this D angle DXA. Angle DXA in here is vertically opposite, so that's 80. Vert op. Hard to write on the screen there. So this is 80. And what else can we say? What we want to do is to have a look at these 4 points. Okay, does the 80 help us there? Not sure, because these 4 points, we might try to show two angles are subtended there of the same size. We could try that. So let's have a look at finding this angle. We could find EAX, sum of angles of this quadrilateral here, 165, 245 from 360 is whatever that is, 115 degrees. Some angles of this quadrilateral down here. So we've got this one here is 115. So what else can we do? Well, we could find this one here. So angle XAB, some angles on a straight line is 65 degrees. Some angles straight line. So we've got that as 65, and lo and behold, up there, angle CDB is 65. Some angles of a straight line again. Therefore, yes, because CB subtends equal angles on the same side of itself. So that's the converse of the angles in the same segment theorem. So that got a bit messy, but I think, can you see the indicator there was because you haven't actually got any angles for the points around the points A, B, C, D, you might use that subtend idea. And we could have shown these two equal. What we ended up showing were those two equal. All right, let's go down to some more now. And here's one, again from Hayes and Harris. Try to draw a big figure and see what you come up with. And let's have a look at it now. All right, a parallelogram is inscribed in a circle. So here we go. Here's a circle. Parallelogram inscribed in a circle. Here we are. So this is a parallelogram. So we've got to have these parallel. So it's a bit rough here. So these are parallel. We're going to call this A, BCD, and these are parallel because it's a parallelogram. Okay, now what can we say? Well, I think what we could do here for a start is to say, well, we want to use the parallel lines and we want to use cyclic quadrilateral ideas. So let's put that across there and call this one alpha 1. So let angle ABD equals alpha 1, and therefore angle BDC will be alpha 2 equals alpha 2, alternate angles. And I haven't looked at the to prove line, which makes it a rectangle, so we'll have to show the angles in the corner are 90, won't we? Now, we haven't done that, we've used those parallel lines. Let's use these parallel lines, and we can say there that beta 1 equals beta 2, and that's alternate angles as well. Okay, beta 1 equals beta 2. And now, what can we do? Well, let's use the cyclic idea. Let's go through each piece of given information carefully. So now we can say that plus that, so that's 2 alpha plus 2 beta is 180, op angles cyclic quadrilateral, bit scribbled. Okay, so therefore alpha plus beta equals 90. Okay, and that's angle B and D, so angle B equals angle D, and then from that figure, because it's a parallelogram, it will be equal to angle A equals angle C equals 90 degrees. Therefore, ABCD, a rectangle. And put in brackets here as required to sign off. Or QED or RTP, one of those things that your teachers have taught you. Okay, so you get the idea. We had a parallelogram. If we show the opposite angles are 90, that makes it a rectangle. How did you go? Follow the strategy. Let's go down to the next one. Here's question 6. OABC is a parallelogram down here. So we should put this in, right? Clearly labelled figure with all the given information. And radius OA, so that's the centre, good. BA is produced, meets at D, yep. Prove that DOCB, so it's DOCB, okay, those out there, is cyclic. Okay, so you'll probably use opposite angles, supplementary, so think about your to prove line and how you might go about it. No lines there are subtending equal angles. We won't construct anything for the moment. We'll try and do it using opposite angles theorem. So, okay, let's have a look. OD equals, I reckon we'll start with OD equals OA, because it's a circle. OD equals OA equal radii. Okay, now, therefore, what have we got? We've got an isosceles triangle, so we can say alpha 1 equals alpha 2 because base angles isos triangle. So see how it's building? This one piece of hidden given information being in a circle, always hidden or equal radii. So now, what can we do? Well, we can say angle OAB, that's this one in here. Let's get in there and use that parallelogram. Angle OAB is 180, take alpha 2 in there, and that's some angles straight line, okay, in there. And then what we can say is angle OCA down here. Angle OCA, OCA equals 180, take alpha, because op angles of a parallelogram abbreviated like that are equal. Okay, so we've got that one. And now I think we've done it. And now we've got, since ODB, angle ODB plus angle OCB equals 180. because one's 180 take alpha and the other one's an alpha. Okay, therefore DOCB is cyclic, op angles supplementary. Okay, as required. So you had to work around that a little bit, and I think it was best to start with the equal radii. Could have started with a parallelogram, but it was harder to see probably what to do with that. Okay, how are you going? Let's keep going now, and we want to go to this one. So I want you to try and draw a diagram and have a go. Pause the presentation so you have a go before you see me do it. All right. Prove that the exterior angle of a cyclic quadrilateral is equal to the interior opposite. We already did this one indirectly back before, so let's go and do it now. So here's A, B, C, D. That's all cyclic there. A, B, C, D. And the exterior angle is, as with triangles, a side extended. So we're trying to prove that this angle alpha, prove angle ABC inside there, the interior opposite, equals alpha. Now, the exterior angle is defined as the angle between a continued side and one of the other sides. So first of all, we haven't got much. We've got a cyclic quadrilateral. So your proof will involve that. Cyclic quadrilateral, we can say, well, first of all, we've got to get in to use it, don't we? So let's find this angle. Angle CDA is 180 take alpha, and that's some angles of a straight line. Okay, in there, 180 take alpha in that little hole there. Now, angle ABC here, angle ABC equals 180 take alpha, op angle cyclic quadrilateral supplementary, just put that one in. Okay, so angle ABC equals alpha. Okay, because we're saying these opposite angles are supplementary. Therefore, angle ABC equals angle CD, I'll call it X or something. Okay, so that then is what we wanted. That is angle ABC. We've done that. ABC is alpha as required, so that's the exterior angle. I didn't need to put this one in here because I changed it to prove line up here. See that? I changed it to an actual tangible thing that we could prove, rather than saying the exterior angle. We said, well, if that's the exterior angle, all we got to do is prove that that was alpha. So when we proved it, we can stop there. All right, so how's it going? I hope you're getting the idea of the strategy, because that's the important thing to be able to do any problem. All right, let's go down to question 8. AB and AC are chords of a circle centre O. This time we've got a nice diagram. Let's have a look, and we're proving that OXAY is cyclic. Again, probably we'll use the opposite angles as supplementary. Let's see what we've got. Well, we haven't got much. We've got a chord and two chords in a circle. So let's start off with a hidden given information. Let's say OC equals OA equal radii. So OC equals OA equal radii. Okay, and OA equals, what else? OA equals OB equal radii. So we've got this here as well. Okay, therefore, now let's have a look at what we can see here. AOB and AOC would be both isosceles. AOB, AOC, isosceles. So do you agree with that? They're all equal. Yep. So therefore, what can you say? OX, now what can we say here? OX down here, OX is perpendicular to AB, because this is the x is the midpoint. Oh, we didn't put that in. That's x, midpoint there. So line from vertex to midpoint of the base of an isosceles triangle is going to be at 90 to it, and OY is going to do the same, okay, because we were told this was the midpoint of that. I didn't mark that in the diagram. That was very bad back up here. I did not mark in that they were the midpoints. So OY is perpendicular to AC. That's a line from the vertex to the midpoint of the base is perpendicular to the base from that old theorem. Now, let's have a look. OXAY, that was this thing, OXAY, and we've just done it, I think. So that means AXO equals angle AYO equals 90. This one and this one, both 90. Therefore, angle AXO plus angle AYO is equal to 180. Therefore, AXOY is cyclic. Op angles supplementary. And that's as required. Okay, so a little bit of a tricky one there. When we got there, you had to know, you had to use x and y as midpoints. And I really should have marked that on the diagram at the beginning. But can you see, when you're stuck, you've got to go and squeeze the given information, make sure you haven't left anything out, and away you go. All right, let's go on. Let's try the next one. So number 9 now. ABCD is a cyclic quadrilateral, and x is any point on the diagonal. X, Y is all. You have to draw a big diagram here. So I'm going to pause it, let you have a go. All right, away we go. Here we have a big circle, and we've got a cyclic quadrilateral inside. So we're going to have something like this. Okay, so we'll go A, B, C, D, always labelling successively either clockwise or anti-clockwise around the figure. Don't cross across it. Okay, and we're told XY is drawn parallel to CB to meet AB at Y. So here, X any point on the diagonal CA, better draw that first. Okay, so let's put X here, and we're going to go across here to Y so that these two are parallel, and then we're going to do the same thing over here so that that's parallel to, no, to the wrong one here. No, it's not parallel to that one. We'll just put that back in. It's parallel to this one down here, and that goes across to Z there. Okay, so that's our complicated looking diagram. So let's make, first of all, let angle ADC equal alpha, so we can start talking about something. Now, I want to use the cyclic quadrilateral thing first. So we're going to say angle ABC equals 180, take alpha, op angles cyclic quad. Okay, so this is 180, take alpha. All right, so what's next? What are we trying to do? We want to prove that x, y, a, z, so that's this one in here. This quadrilateral inside is cyclic, so I didn't look at the to prove line. It's probably just going to be opposite angles are supplementary, I would guess. Now let's do something else. What? Let's say here. Let's call that alpha 1. Alpha 1 equals alpha 2. I'm going to use those parallel lines next. Alpha 1 equals alpha 2. So they are corresponding angles. So it's easier to put in those alphas. Alpha 1 equals alpha 2. Now, what we can say is this angle in here, we're going to use these parallel lines now, just going through them one after the other. AYZ equals 180, take alpha, corresponding angles for those other two parallel lines. And I think we've done it, because we've got that angle and we've got this angle. Therefore, we can say angle AZX plus angle AYX equals alpha plus 180 take alpha, which equals alpha. Therefore, AYXZ, and I better put it the same way as what they put it up there, XYAZ is cyclic, op angles supplementary, and as required. So we had to sneak up on that one a little bit and use both pairs of parallel lines. That was important. Okay, how are you going there? Let's go on now. For number 10, you've got to draw your own figure again, so that's a bit of a problem. So let's draw this. ABC is an isosceles triangle. So here we go. ABC is an isosceles triangle, and what we've got to show is that BCXY is cyclic. Let's have a look. Well, first of all, AB equals AC, so we've got that. The angle bisectors at B and C, so that's B bisects there, meet at X and Y. So we better put that in. Alpha 1 and alpha 2, beta 1 and beta 2. A good well-labelled diagram, large enough. Okay, so we'll put those in. So we should put it here, angle ACB equals angle ABC equals alpha. That was given because it was a bisector. And also angle YBX equals angle CBX equals beta. That was given as bisectors. Now what can we say? We want to show that BCXY is a cyclic quadrilateral. So what can we say now with these two? Well, let's have a look. We haven't used the isosceles. Okay, so now we can say these two angles are equal. So 2 alpha plus 2 equals 2 beta. Okay, 2 alpha equals 2 beta. Base angles isosceles triangle, and therefore alpha equals beta. Alpha equals beta. That is XY subtends equal angles at C and B on the same side. Therefore BC XY is cyclic. Okay, and that's the reason there, as required. So this time we've actually been able to spot two angles sitting on that side XY, not the cyclic idea then. Okay, so how are you going? Let's see if you've got any marks for those 10, and there's a few more to come. So what I'll do is just pause it there and come back in part 2 of this presentation and give you the answers to those remaining questions. So it's cheers for now. I'll catch you in that next presentation.